Okay, so the question is saying that for a non-negative real number alpha, let the square root denote its non-negative square root. Consider the sequence this, and this. Okay, so I have to find the lim sup of xn. So now note that the question is saying that root alpha denote its non-negative square root. This means that whenever the thing come out of this square root, this will be positive always according to question. Okay, so we need to know that, and we need to keep this in mind. Okay, so now if I calculate sum of the terms of the sequence, then x1 is given 1, so no need to calculate x1. So x1 equal to 1, x2 is equal to root 2, and root 2 is equivalent to 1.41, and x3 equal to this, x4 is equal to this, and x5 is equal to this, and x6 is equal to 1.13. So note that this is x4 is less than x2, x5 is less than x4, and x6 is less than x5, and so on. Okay, so from here we can notice the pattern that x1 is less than x2 is less than equal to x3, and x3 is greater than x4 strictly. Okay, x4 is strictly greater than x5, and x5 is strictly less than x6, and so on. Okay, this means that this sequence is decreasing sequence. Okay, so I can write in general that xn is less than equal to root 2. Okay, now 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 xn plus 1 is equal to xn plus 1 is equal to 1 plus xn square upon n. Okay, so now if I replace n plus 1 by n, then so let us calculate. Let replace n plus 1 by k. Okay, then I get xk is equal to under root, wait, under root okay, under root 1 plus xn means, so from here n plus 1 is equal to k. This means n is equal to k minus 1. Okay, so xk minus 1 square upon n means k minus 1. Okay, so now if I replace k by n, then xn is equal to under root 1 plus xn minus 1 square upon n minus 1, and this was for n greater than equal to 1. So this will be for n means k minus 1 greater than equal to 1. This means for every n minus 1 greater than equal to 1. This means for every n greater than equal to 2. Okay, so I am getting the expression for xn. Okay, so this is xn. Okay, therefore xn is equal to under root 1 plus xn minus 1 square upon n minus 1 for every n greater than equal to 2. Okay, now note that as n is greater than equal to 2, this means this thing is always positive. Okay, and we are scaling this term, so this xn minus 1 will be always a positive thing. This is always positive 1, 1 is always positive, so the thing under the under root is positive. Okay, so this is under root some positive thing. Okay, or note one thing, that we are getting under root 1 plus some positive thing. Okay, 1 plus some positive thing. This means whenever this whole thing comes out of the under root, this will always be greater than 1. Okay, okay, okay. So this means, therefore, xn is always greater than 1 for every n greater than or equal to 2. Therefore, as we know that xn is less than or equal to root 2, so from here we can say that 1 is greater 1 is less than xn, and xn is less than or equal to root 2 for every n. Okay, since here we have n greater than or equal to 2, but this is an infinite sequence, so there is no impact of a finite term which we neglect. Okay, this means this thing work. Okay, so now from here, wait, so from here I can say that xn is a bounded sequence. Okay, now this thing is done, that xn is bounded. Okay, so now I need a new slide. So in this slide I will prove that xn is decreasing. Okay, now as therefore, sorry, we have, since xn plus 1 is equal to under root of 1 plus xn square upon n. This means, therefore, wait, okay, so this means xn plus 2 minus xn plus 1 is equal to, this will be equal to 1 plus xn plus 1 square upon n plus 1 minus under root 1 plus xn square upon n. Okay, so now if I solve this by rationalizing, then I get 1 plus xn plus 1 square upon n plus 1 minus 1 plus xn square upon n, and in the denominator I will get 1 plus xn plus 1 square upon n plus 1 and its square root. Okay, so its square root plus 1 plus xn square upon n and its square root. Okay, so now note that this whole thing is positive. Okay, this whole thing is positive, this thing is positive also. Okay, so so the thing which comes out of the square root is positive also. From the question we know that, from this statement. Okay, so this is positive, and we are summing these two. Okay, so the thing in the denominator is positive also. Okay, so name this k, and this is positive. Okay. Okay, therefore if I erase this and write k here, this will be convenient for me. So this is k, and k is positive. Okay. Okay. Now if I calculate this, so if I remove the bracket, I will get this, and minus of this, -1 and +1 will be cancelled out, and I am left with this thing. Okay. Okay. So now if I put the value of xn plus 1 here, then I get this is equal to 1 upon n plus 1, and I'm putting the value of xn plus 1 square. So if I square this, so this square root will be removed from here. Okay, so this will be 1 plus xn square upon n minus xn square upon n, and in the denominator there is a positive thing. Okay. Okay, now I have to solve this. Therefore xn plus 2 minus xn plus 1 is equal to 1 upon n plus 1. So I am multiplying this inside, so I get 1 upon n plus 1 plus 1 upon n into n plus 1 and xn square minus xn square upon n. Okay, and in the denominator there is k, which is positive. Okay, so I get this thing. This is equal to 1 upon n plus 1 plus xn square upon n, 1 upon n plus 1 minus 1, and in the denominator there is k, which is equal to 1 upon n plus 1 plus xn square upon n, and this is 1 minus 1 minus n upon n plus 1. Okay, and upon there is, in the denominator there is k, which is positive. Okay, so this one goes, so I get 1 upon n plus 1 plus xn square, so these are cancelled out, there we will left with minus n, and minus n goes, so I get minus xn square upon n plus 1. Okay, and in the denominator there is a k, which is positive, and now I will get 1 minus xn square upon n plus 1 upon k, which is a positive thing. Now note that, wait, now note that from here, if I square both sides, I will get xn square is greater than 1. This implies 1 minus xn square is less than 0. Okay, so I am using this inequality here. Okay, as this is less than 0, this is a positive thing, and the denominator is also positive. So overall this is negative thing. So this is less than 0. Therefore xn plus 2 minus xn plus 1 is less than 0. This means xn is decreasing. Okay. Okay. So I have proved this in general way. We can see that from here that it is decreasing, but I have proved this that this is decreasing in the terms of n. Okay. So now note one thing, that xn is decreasing, and and xn is decreasing, and xn is bounded below from here. Okay, xn is bounded below. Xn is bounded below. It is bounded, but uh, we need to know that this is bounded below. And from here I can also say that xn is bounded. This means xn is bounded below and xn is, so from here I can say that xn is bounded below and above also. Okay, okay, and above. Therefore xn is bounded sequence. Now, we need to know that a theorem which says that if xn is decreasing sequence, then it is convergent if and only if it is bounded below. So I am using this theorem here, and decreasing plus bounded below, as we know that. Therefore xn is convergent. Okay, so we know that xn is convergent. Therefore xn is convergent. Also we know that xn is bounded and xn is convergent. Okay, so we know a theorem which says that a sequence xn in R is convergent if and only if it is bounded. Okay, we know that our sequence is bounded, and lim sup of xn is equal to lim inf of xn, or we can say that limit of xn is equal to lim sup of xn and lim inf of xn. So in general way we can say that if a sequence is convergent, then lim sup of xn is equal to lim sup or lim inf of xn is equal to limit of xn. Therefore using this that theorem, we know that limit xn as n tend to infinity is equal to lim sup of xn is equal to lim inf of xn. So this means if I calculate the limit of sequence, I will get my answer, which is lim sup of xn. Okay, so okay, now from here, if limit n tending to infinity xn is equal to L, then xn plus 1, xn plus 2 and so on will go to L. Therefore applying limit both sides of this sequence, we get lim of xn plus 1 means L is equal to under root 1 plus limit xn square upon n. Now we know that xn is bounded, so this term is always a bounded term. Okay, this is bounded. So if n tend to infinity, so this whole thing will be 0. So I get L is equal to root 1 plus 0. This means L is equal to under root 1. This means 1, as given in question that root of 1 is always positive. So root of 1 is 1. Therefore L is equal to 1. So this means 1 is equal to lim sup of xn, which is equal to lim inf of xn. Okay, so we get our answer. Therefore 1 is true, 2, 3, 4 and false. Okay,